In this video, I'm going to cover black bodies, Wien's law, and Stephan-Boltzmann's law as it applies to thermal energy, as well as its applications in stars. Please take a moment to read the success criteria I plan to cover. So first, let's talk about this idea of a black body. Now, we don't just mean the color black. It actually has specific properties. This is what Max Planck was looking at when he first did his work that then Einstein was looking at and did his photoelectric effect. We're talking about the idea that a black body absorbs all of the EM radiation that lands on it. The reason why we see it as black is because it doesn't actually reflect any of the light that lands on it. So if all the light lands on it is absorbed, nothing goes back to our eyes, and our eyes interpret that as black. So a perfect absorber will also be a perfect emitter. Now, not everything is perfect like that, and that is just in theory. So we have this value called an emissivity, and it can help us say how close is it to a black body or how far away it is. So we get a value between 0 and 1. 1 being perfect, 0 being it reflects everything and doesn't absorb anything. If our emissivity then is 1, our perfect value, we're going to call that body a black body. Now, when an object gives off radiation, and typically at this point we're talking about thermal radiation, because this does come up typically in our thermal physics sections, but it also does come up in our section with stars as well. And in that case, most of what we're looking at, it would be visible light. But remember, most telescopes nowadays aren't looking at visible light. They're looking at different parts of the EM spectrum. Well, what Wiens has done is he looked at the intensity of the wavelengths given off. And he's done this graph for us. Now notice here, the intensity of something that's really hot has a peak way up here compared to down here, which is cooler at only 3,500 K. I think you're probably familiar with this. If we talk about how to heat up a metal, you know that the hotter it gets, the different colors it's going to give off as it gets hotter and hotter. Well, that's what we're looking at here. The temperature is actually going to have a peak at a different spot. Now, we have this equation, it's in our data booklet, and we can see there's a relationship between the maximum wavelength being given off and its temperature. If I take these two values together, they will give the constant 2.9 times 10 to the minus 3 meters times Kelvin. You can see here my peak here, as my temperature rises, I do get a shorter wavelength. The one nice thing about this value given to us like this in the data booklet is it's telling you, because the units are right here, my wavelength has to be written in meters and my temperature must be in Kelvin. Now we also have this other law, the Stephan-Boltzmann law, and it's going to link the luminosity or the total power given off by a black body and its temperature. Now it's not quite so straightforward. Our temperature is now to the power 4. So, in our data booklet, we have the luminosity, which is another way to say the power, is going to be sigma, our Stefan-Boltzmann's constant. This is my favorite. Look, 5.67 times 10 to the minus 8. I just kind of like it. Times the area. This will be the surface area. And don't forget, for a sphere, that's going to be 4 pi r squared for the surface area of a sphere. And then temperature in Kelvin to the power 4. Now I've got here E as the emissivity value, and that's because we actually could have right there an E. Right now my equation is written as E equals 1 for a black body, so that's why you don't see it. But we could have questions that ask you to talk about the luminosity or power of something that's not a perfect black body. So let's bring this all together and do a question. Determine how much energy Betelgeuse radiates each second. So we have our surface temperature here, and we have a radius of the star. Now, energy per second, that's actually just power. And if you remember, power is also called luminosity for a star. So I'm going to use my equation. L is sigma A temperature to the power 4. And if I pick up my handy dandy calculator, I'm going to get 4.5 times 10 to the power 30. And the units will be the units of power, or energy per second. That's watts. I'm going to write it up here because I'm going to need space for my next question. All right, in part B, it says, what's the brightness? Remember, that's also another way to say the intensity of a star at its surface. Well, I've got in my data booklet that the brightness is going to be the luminosity over 4 pi d squared. And now d is going to be the distance from the center of that star. So at its surface, we just calculated the luminosity is 4.5 times 10 to the 30. I'm going to need that over 4 pi and now this radius squared because we're at the surface. If I pick up my handy dandy calculator, 4.0 times 10 to the power 6. And this will be in watts per meter squared. Again, I'm going to write that up here. Now, it says, what's the brightness at a location that is this far from its surface? Well, notice it's doubled that distance. So I could do two things. I could first of all do brightness as luminosity over 4 pi d squared. Putting my numbers in, my distance is now 6 times 10 to the 11. And I get a value of 9.9 times 10 to the power 5 watts per meter squared. Now, we also know that this relationship between the brightness and the distance from the center is an inverse square relationship. So if the initial value was 4, if I double my distance, then my brightness will reduce by a factor of 1 over 2 squared, or 1 over 4. And 1 over 4 times 4.0 times 10 to the 6 is going to be 1 times 10 to the power 6, which is basically what I have here. Part D. What major assumption was used in calculating the luminosity? Well, we assumed that the emissivity was equal to 1. It's a black body. And finally, it says compute the luminosity radiated by Betelgeuse if its emissivity is measured to be only 0.9. Now, if you didn't get part D, this really should have been hint, hint, nudge, nudge. What do you think where does this come from? So that means the real power is going to be 0.9 times the theoretical value we had. So 0.9 times 4.5 times 10 to the power 30. Picking up my calculator, I get 4.1 times 10 to the power 30 watts. So please read the success criteria one more time. I hope that helps you say yes to all these pieces.